No need to copy anything. This one, everything there. Hey, where are your notes? Okay, now let's go to page 15 of your notes. Okay, now, in page 15 of the notes, they are proving some results involving addition and multiplication of complex numbers in polar form. Okay, but the proof there, as you can see, are quite complicated. Okay, so I'm going to give you a much simpler proof involving exponential form. And that is also why I skipped this page first. Okay, now, so what are the things I want to discuss? Now, suppose I have two complex numbers. Okay, I have two complex numbers, they are written exponential form. By now, you should be able to draw parallels immediately to how they will look like in polar form. Okay, okay, now, if I have these two complex numbers and I multiply them by each other, okay, then what I'll get is this. Okay, and then let me rearrange the terms. Okay, and then apply law of indices. Okay, follow? Right, okay, so now let us just focus, okay, our attention on Z1, Z2, okay, and what's all the way on the far right. Okay? Okay, so let's focus on this now. Okay, what can you now tell me about the modulus of Z1 times Z2? The modulus of Z1 times Z2 is what? R1 times R2. Right, but what's R1? What was R1? R1 was the modulus of Z1. R2 was the modulus of Z2. Okay, so just from this result, I can immediately conclude that the modulus of the product is equal to the product of the moduli. I repeat. Okay, I repeat. The modulus of the product is equal to the product of the moduli. Okay, which is exactly what you learn in real numbers. Nothing has changed. So remember, I always say this. Complex numbers is merely an extension for the real numbers. Whatever held in real numbers should also hold. Okay, in complex numbers. Okay, the next point will not, you did not see this in real numbers, right? The argument. Okay, can you give me a similar conclusion about the argument? What can you say about the argument of Z1 times Z2? It's theta 1 plus theta 2, right? But what was theta 1? The argument of Z1. And theta 2 was the argument of Z2. Okay, so immediately, I also have this result. Okay? Okay, argument of Z1 times Z2 equals argument of Z1 plus argument of Z2. Okay, so you have to change from times to plus. Okay, so you need to adjust your thinking a bit. Okay, if not, you made a common mistake that argument Z1 times Z2 equals argument Z1 times argument Z2, which is wrong. Okay, but maybe to help you, I have a trick to help you remember this easily without making careless mistake. Okay, what have you learned in secondary school, right? That changes from times to plus 1. What? Log. Right, log, 木头, okay, which is Chinese for log. Okay? You remember this or not? Remember this? You like it? Okay, don't like it also too bad. Okay, so just remember this. Argument works like logarithms. Okay, when I talk about arithmetic operations, of course. Okay, so can you just put that down? Arguments work like logarithms, but only with respect to arithmetic operations. Okay, it doesn't happen all the time. Okay, so this will hopefully help you remember more easily. All right. Okay, so now let us practice our knowledge. Can I change slide already? Okay, okay, change. Okay, so some of the other results I can extend to. Okay, so you can see from here again, works just like logarithms, right? Okay, the modulus one, nothing new to you. You learned this before. Okay, I can also say a few things about powers of z. So these are something like I say. Again, works just like logarithm for argument, right? Okay, from the last part, we can deduce this. Okay, because on the left-hand side, this is actually z to the power of n if my r equals to 1. Okay, on the left-hand side, on the right-hand side, because I knew that argument of z to the power of n is n times of theta, n times of argument of z, I can therefore also write this. The modulus is still 1, so there's no r. Or that appears like there's no r. Okay, so this is what we call the De Mor's theorem. De Mor's theorem, not De Moivre's theorem. Please don't insult my mathematicians. Okay. Okay. This will be on page. De Mor's theorem is on page 18. Okay, but I'm not going to really explain this in full. Okay, so just remember this. Sometimes there are questions appearing in your tutorial exam. Use the De Mor's theorem to show something. Then you're like, what am I supposed to do? Okay, just remember this. De Mor's theorem and Euler's formula, they're actually talking about the same thing. Because I can always derive one from the other. Okay, I can always derive one from the other. Alright, okay, next. Okay, can you just quickly work this out? Right? Example 6.2.1. I give you 1 minute. You have to learn to draw your Argand diagrams quickly. Yeah? Okay, so draw the Argand diagram, locate the point, identify the quadrant, apply basic angle, etc., etc., etc. Still not used to your special angles by now, please go and do something about it. I'm not kidding when I talk about that. Okay? Okay, so you should see, I'll just show you the solution, you check. Okay? Okay, now after you add the angle, right, to each other, okay, you are going to get 7 pi over 6. Okay, so you work as you check, as you listen. Okay, we have to do it a bit quickly now. Okay, you're going to get 7 pi over 6. Okay, then you recall in the previous lecture. Okay, I said by convention, we will always put our angles into this range. This is what we call the principal range. Okay? Now, is 7 pi over 6 currently in our principal range? Yes or no? No. Yes or no? 7 pi over 6, is it currently in our principal range? No. Okay, so if it's no, then the next question is it too big or too small? Too big. Okay, if it's too big, how do I bring it back inside the principal range? Do you know how? 2 pi minus. Okay, not 2 pi minus. Minus 2 pi. Okay, because why? Remember, I take any angle. Okay, so 7 pi over 6. Seven pi over 6 will be here. Now it's outside my principal range, so I must go back by 2 pi. 2 pi is 360 degrees. Okay, if I go back one full revolution, I come back to the same angle. Okay, and so that's what I'm going to do now. I'm going to subtract 2 pi from this. Okay, but can I say that 7 pi over 6 equals to 7 pi over 6 minus 2 pi? Can or not? Can I say that numerically speaking, 7 pi over 6 equals to 7 pi over 6 minus 2 pi? Cannot, right? Because numerically they are not the same. So now how? They are like, die. I want to say minus, but then I don't know how to present properly. Okay, so how you should present properly is instead of an equality sign, you put in a congruent sign. Okay, so please don't go and write. And then later your tutor check your assignment. How come my student tell me that 1 plus 1 is 1 equals 2? Because if you say 7 pi over 6 equals 7 pi over 6 minus 2 pi, you can prove that 1 equals 2. Okay. Okay, so you have to put in the congruency symbol to signal to us you are considering it as an argument and you wish to bring it to the principal range, you get the answer of negative 5 pi over 6. Okay? Okay, so this will appear a lot later when you are multiplying or dividing by complex numbers. So for example, this one, okay, which I will just quickly run through. Okay, now, I wish to express the following in exponential form. Okay, so what I do is this. First, let me express both the numerator and denominator in exponential form. Alright? Okay, and then I have this. Okay, I have this. Okay, by laws of indices. Alright, is it already inside your? Okay, not quite. Okay, so after I do this, I now have the exponential form. Alright, so when I do multiplication and division of complex numbers in exponential form, I will have to repeatedly apply my laws of indices. That is why at the start of today's lecture, I record two things for you. Although you're supposed to record yourself. Okay, first was the law of indices, second was the Maclaurin series. Okay, next. Okay, next.